The first learning objective in the PS2-3 standard, which is all about impulse momentum theorem, is I can use the mathematical model of the impulse momentum theorem to predict the average force experienced, change in velocity, or time interval from the same characteristics of a collision. The active verb of this learning objective is predict. So essentially, what we're going to be doing is taking the impulse momentum theorem equation and then rearranging it, plugging in values, and solving. We've done this with Newton's second law before. Rearrange, plug in, solve. Before we could talk about the impulse momentum theorem, we need to talk about what impulse is. What is the definition of impulse? The definition of impulse is that it is defined as the change in momentum. So impulse is just change in momentum. Strangely enough, we use the capital J to represent change in momentum. Mathematically, we can write J is equal to delta P. Well, delta P, of course, meaning the change in momentum. That's going to equal the change in, well, what is momentum but mass times velocity? So impulse is equal to the mass of an object times the change in velocity. So it's basically how much does the velocity change of an object, and it's because a force is being applied on it. Since velocity changes, since we're talking about velocity changing, since impulse is a change in velocity times mass, velocity must be changing, and if the velocity ever changes, the object must be accelerating. That's the definition of acceleration, is a change in velocity over time, or the rate of change of velocity. If velocity doesn't change, then the value for acceleration can be 0. So if an object is accelerating, then we know from Newton's first law that it must be experiencing a net force, a net external force. So impulse is caused by a force. From our experience, we can easily tell that a larger force would cause a larger change of velocity. If you're hitting harder, it's going to change the velocity more. So we know that there must be some kind of relationship between force and impulse. Larger force means larger impulse. But what is the actual mathematical definition of this? Well, first, let's start with the idea that impulse is equal to the mass times the change in velocity. Then, we're going to do something odd. We're going to multiply by 1, but not just any 1, a fancy one. We're going to multiply it by the change in time over the change in time. Since it's the same value over the same value, we're going to get a value of 1. And we can multiply anything by 1 and not change it. So this is a completely legal thing we can do. We can do this, no problem. So that equals mass times. Now, what we're going to do is, instead of multiplying by this fraction, let's take the bottom of this fraction and move it underneath the change in velocity. This is completely legal to do. So now we have mass times the change in velocity over time times the change in time. Now, this change in velocity over time should look very familiar. Change in velocity over time is the average acceleration. So now what we have is we have the mass times the average acceleration times the change in time. And again, this part should look familiar from our studies of Newton's second law. The mass times the average acceleration is going to equal the average force. Average force times the change in time. Or in other words, the average force being applied to this object, average external force, we should be clear, being applied to this object, times how long that force is being applied to this object, is going to equal our impulse. And this is the impulse momentum theorem. The change in momentum, which again can be represented with J for impulse, is equal to the average force, external force, to be clear, the average external force experienced by an object times how long it is experiencing that force. The units for impulse and momentum are both newtons times seconds. We can see that also from the force times time. We're going to have a newton times a second in units. Let's go over an application of the impulse momentum theorem. A car with mass of 500 kilograms hits a wall going 60 meters a second. The collision lasts 0.5 seconds, so about half a second. What was the average force that the wall exerts on the car? So let's start with our equation, our impulse momentum equation. The change in momentum is equal to the average force times the time that the object is experiencing the force. And this question is asking us to solve for the average force. So what we're going to do first is rearrange this equation such that force is by itself. So what we get is the average force is equal to the change in momentum over the change in time. So that equals, if we break up this delta into what it means, that equals the mass times the final velocity minus the initial velocity, all over time. Now, why is it not time minus time? Because this is change in time. Well, technically it could be. It could be final time minus the initial time. But why would you set the initial time to anything other than 0? So that all goes away, and we can just write time. Plugging in some values, we get 500 kilograms times 0 minus 60 meters per second. Why is that the case? Well, what is the final velocity of a car that hits a wall and stops? Well, it's going to be 0. So we start with 0 minus 60 meters a second. Overall, we're going to have a negative number inside these parentheses, which means overall the numerator is going to be negative. And if we have a negative numerator and a positive denominator, we're going to get a negative number in our answer. What does this negative number even mean? Well, we actually didn't do one thing while applying this problem. We forgot to apply the positive or negative direction. So we're going to apply the positive direction being towards the wall. And the reason we did that is because we used a positive value. I know it has a negative sign in front of it, but that comes from the subtraction. We're going to use a positive value for the initial meters per second, the initial velocity. That kind of goes against convention. Most of the time the convention is to the right is positive and to the left is negative. But we can do this. It's perfectly legal and fine. What we're going to get in the end is a negative force. A negative force would just mean that this force is acting to the right. And we could have guessed that because the idea is that this wall is going to stop the car. So in order to stop the car, it's got to push to the right because the object is going to the left. So the last problem came pre-solved. For this problem, let's work on it together. We have a space probe that is experiencing a 0.1 Newton force for an entire year. Assuming the mass of the probe is 1,000 kilograms, how fast would it be going after that year? What I want to point out is that this is a really heavy object. 1,000 kilograms, it's pretty heavy. And this force is really small. This force is incredibly small. So this force is really small, and the object is really large. Its acceleration is not going to be that high. We can use Newton's second law to figure that out. But what's key about this is that we're doing this for an entire year. So although the force is very small, we're applying that small force over this time span of an entire year. We'll be surprised on how fast this thing is going at the end. And this is actually really how space probes are potentially designed. Whenever a scientist or engineer builds a space probe, they can build them with actually very little thrust, very little force pushing them. They can have something be very, very efficient, but have a very low thrust, because over a long period of time, it's going to apply that small thrust very efficiently and get to a high speed. So let's start this problem like we did with the other one. We're going to start with the equation for impulse momentum theorem. Now what we're going to do is we're going to try to figure out what we're solving for. Well, the question asks for what is the final velocity. So we're looking for final velocity, but I don't see final velocity in this equation. Well, that's because it's inside of the delta p, the change in momentum. Let's write the change in momentum as the final momentum minus the initial momentum. Now, one thing that was not stated in this problem is how fast is this going to begin with? We're going to assume that since it's not stated, we're going to assume that it started at rest. This probe is not going anywhere at time equals 0. So its initial momentum is 0, so we can strike out that whole term, and then we just have the final momentum. Now let's break up that final momentum into what it actually represents. It's the mass times the final velocity. All of that's going to equal the average force experienced times the change in time, which we could just write as time, since we're going to let initial time be 0. Now we can see what we're solving for. We are solving for the final velocity. So let's rearrange this equation for the final velocity. And now let's plug in some values. Before we can plug in some values, we need to realize that we were not given the time in seconds. you cannot put 1 year right here because everything in physics is done in seconds for time. So what we're going to have to do is figure out how many seconds there are in a year. And of course, this is something you could technically look up. But instead of looking this up, we're going to figure this out using some dimensional analysis. So first off, we're going to start with 1 year. And then what we're going to do is multiply that 1 year by 1 year on the bottom. And on the top, we're going to go 365 days. That cancels the years and gives us days. But we're going to continue from there. We're not just going to stop. We're going to now go from days to hours, hours to minutes, and then finally minutes to seconds. So in the next step, we put days on the bottom because then that's going to cancel the days and give us hours. And on the top, we're going to have hours, and it's 24. We're going to repeat this pattern, putting the unit we have before on the bottom and the unit we want on the top. In this case, it's going to be 60 minutes and then 60 seconds. So in the end, we're going to convert all the way from years to seconds by just multiplying 1 times 365 times 24 times 60 times 60. And in the end, we get a monumental 31,536,000 seconds are in 1 year. So now we have everything in the correct units: newtons, kilograms, and seconds. In the end, we get that this object, this space probe, is going 3,150 meters per second. For such a small force, this thing got it to go pretty fast. That is approximately over 7,000 miles per hour. For your practice, I have a ton of practice problems. I would recommend choosing at least 3 of these practice problems. Try to choose ones that are asking for different values in the end. And solve it. Now what's useful about this page is that at the bottom we have all the answers for it. Obviously not the work. So solve them and show your work.